Hi there. Now that we know how to set condition codes, let's see how we use branch instructions that depend on these condition codes to modify the control flow of your program. Okay? So x86 supports several branch instructions of the type J for jump, X, and X can be a bunch of things here. And the first one is an unconditional branch, means that it jumps no matter what. There's no condition. So the condition for the branch is always true. It's 1. So that's the JMP instruction. But let's pick another one here. For example, if you have JE here. JE only jumps to the destination instruction address if the ZF condition register is set to 1, which is used, for example, when you do an equality comparison, right? So if you do a compare A and B, for example, the ZF condition code is going to be set to 1 only if they're equal. Because if you recall, the compare instruction performs the difference. The difference is 0. It happens that the numbers are the same. And then there's a bunch of other jump instructions that they encourage you to take a look and see how their conditions work. Now we're going to jump into an example. So this piece of code here, ABS diff, does the following. It receives X and Y as a parameter, and then returns the absolute difference between them. And the way we do that is by first comparing if X is greater than Y, and if so, the result is X minus Y because X is greater. So, and otherwise, it does Y minus X in case Y is greater than or equal to X. And this is the assembly code in IA32 that implements this piece of code. And the first thing to note here is that we are using two branch instructions, two jump instructions. This first one here, JLE, just jump if less than or equal. And note that there's a new thing here. This is a .L7. That's what's called a label. A label simply specifies a location in your code where the jump is going to jump to if the condition evaluates to true. So if the comparison does lead to a less than or equal result, the control flow is going to, so the program execution is going to go to here. When it reaches this instruction, it's going to go and jump here. And then this instruction is going to be executed. Now there's an unconditional jump here that just branches to .L8, a different label, to return from the function. Okay? So you might have a hard time actually mapping this code directly to this assembly implementation here, because there's some other thing that's going on here. Let me show you what. First, one way of looking at this is to put a bunch of Gotos. Let's convert this program to use Gotos to make it easier to see the translation to assembly. And by the way, we do not recommend using Gotos in your code. You can use Gotos in C, but it's generally considered bad coding style. But we're doing here just to make it clear how the translation happened. First, note that the expression in the comparison here changed from X greater than Y to X less than or equal Y, because this is determining whether we should jump to the else position, which is the invert condition. Okay? And if so, we execute the else. And whenever we're done with the else, it comes back to the exit, which is this part here. Okay? So the exit here. Now, if this evaluates to false, we're actually executing the then part of your if. So that means that's called the fallback. When you do not take a branch, it's called the fallback. And in this case here, the fallback is the then position. Okay? So at high level, the way to think about this is that we converted this such that we jump over the then part of your if condition. Okay? And execute the else only if the condition evaluates. Great. So let's look at this example step by step. Now note that we are looking at the C code that's converted to use Gotos now. These two instructions here are just reading X and Y, putting them in EDX and EAX respectively. And now that's when we're performing the comparison. Now that X and Y are in EAX and EDX registers, we are comparing them. Okay, so we're comparing X and Y. That's implementing this comparison here. And if this comparison happens to evaluate that X is less than or equal Y, then we jump to L7 to implement the else block. Now let's see how the else block. Okay, so now if the jump does not happen, we're executing this part of the code. We're going to execute this instruction. Here's how it's implemented here. Just how we implement it here. So this sub instruction here does EDX equals EDX minus EAX. So it's essentially doing X minus Y. And then it gets the result and stores it in EAX. And the reason we store into EAX is because that's where we put return values for the function, so that we can actually return the results. Now, the next step here is to implement the else part of our block. And that's going to implement x minus y. And we use another sub-instruction here, except that now see that the parameters are inverted compared to the other one. Now, what we're doing is EAX equals EAX minus EDX. And then from there, we just jump to L8, that's going to be returned. And note that we did not need to copy the result to EAX such that we can return it, because the result was already in EAX. So let's look at conditional expressions in general and see how their translation happens. Well, in C, you can write the following conditional expression. You can put a test here, which is any condition, for example, x greater than y. And then we put the then expression, means that if this test evaluates to true, we're going to return the then expression. Otherwise, we're going to return the else expression. So one way to implement the code we just showed you is to say compare x, whether x is greater than y, and if so, we return x minus y. Otherwise, we return y minus x. So, and here's the Goto version of that. So we are evaluating the opposite of this expression. So in this case, we're just going to be the complement of that expression, and execute the else in case it evaluates to true, and then otherwise we're going to execute the then. So it does exactly what we just saw in the previous slide. So now you might be asking, how can we make this more efficient? Just so we can implement this simple conditional expression, we are inserting a bunch of branches in our code, a bunch of jumps. And this is not very efficient. Branches tend to be expensive, especially in modern deeply pipelined processors. So x86 supports a special, x86-64 supports a special type of instruction that solves that problem. It's called a conditional move instruction. So what conditional move does is it moves a value from one register from the source to the destination only if a certain condition is met. And this condition are the same ones that we use for jumps. So that means we can rewrite this code here in a way that we perform the comparison, and depending on the result of the comparison, here we do a move. So we say we do move less than or equal. So essentially, we only move the value from EDX to EAX if the condition is satisfied. So we can implement exactly what we just showed in the previous slide without any branches. So we do the two subtractions here. We subtract y from x and y from and x from y, store them in EAX or EDX, and then here we only move EDX to EAX if the condition gets set, and then we just return because we should put the return value in EAX. Isn't that great? So now this is a way of executing conditionals, implement some conditional blocks without using branch instructions. So this can be a big win in performance in several cases. So one last thing I want to show before ending this video is how addressing actually happens. Addressing of the destination instruction in branches. Okay? And often the destination is specified in what we call in a PC relative way. It means that the instruction specifies an offset that should be jumped to relative to the current instruction address. So in this example, we have this JE instruction that jumps to, that's located in address 0x102, and it jumps to 0x172. But note that the destination here is specified as 0x70, because this address here is computed as 0x102 plus 0x70, which is this value here. That's called PC relative. And the reason that this is so important is because now we can relocate this block. We can just change, for example, here we change it to a different address, and now we still have this compatible, because if we change where the code is, since everything is relative, you're not going to have to recompute the targets in the branches in your code. But note that some branches have absolute addresses. In that case, they're not relocatable. See you next time.